Okay, good afternoon, everybody. My name is Mike Waldridge. I'm Head of Department of Computer Science, and it's my very great pleasure to welcome you to the Trinity Term Straight Lecture. And in fact, as you will surely have noticed, we have an exciting double bill this afternoon because the Straight Lecture will be followed by, after a half-hour break, by the Lovelace Lecture. But first, the Straight Lecture, and it's my enormous pleasure to welcome my colleague Sarit Kraus from Bar-Ilan University in Israel. Sarit gained her PhD in 1992, one of the earliest PhDs in the area of multi-agent systems, and it was a system that played the game of diplomacy, as I recall, and this system established many of the techniques that went on to define Sarit's career. Although her most cited work is in the area of non-monotonic reasoning, the so-called KLM semantics, in my community she's best known for her work on automated negotiation, automated bargaining. And this is an area which she has really identified and made as her own. And over the last 2 decades, she's been the one person in that community which has really championed that area and pushed it forward very determinedly towards the goal of building agents that can negotiate and bargain proficiently with people, which is what she's going to tell us about this afternoon. She's won a string of awards, including the IJCAI Computers and Thought Award, which is the most prestigious award that can be given to an AI researcher under the age of 35. That was now some time ago, though, Sarit. We've both got a bit older since then. But has then gone on to win a number of other awards. She's a AAAI fellow, a fellow of the European Association for AI, and is a recipient of the ACM Autonomous Agents Research Award in 2007. She's a good friend and a very close colleague. We've published many papers together, and I look forward to publishing many more. She suffers, as I do, from the current affliction of being a head of department. But when we're both through that, we'll both get back to it. So, Sarit, it's an enormous pleasure to welcome you to give the Straight Lecture. Thank you.
Yes, thank you, Mike, for your kind words. And I would like to tell you what I like to do. I like to build agents. I like to build agents that interact proficiently with people. You know, in this room, I probably don't need to say what is agent, but I'm looking at autonomous intelligent systems that plan, is adapted, able to learn, cooperate with people, can face adversary. But especially I'm interested in these agents that interact proficiently with people. Now, what can this agent do? They can help people, they can replace people, and they can be used to train people. For example, supporting people. We have a project with General Motors where the agent was helping and supporting a driver in electronic cars to reduce the use of energy by helping him set the air conditioning and the climate control system in an intelligent way. We had a system with Milin Tambe that is still since 2007 in the LAX airport, helping people to decide where to put random checkpoints to save, you know, and if we're talking award, we got an award from the Homeland Security of the system. I'm really proud of it. They are really using it. And on the other hand, I would like an agent that will whisper in my ear and help me convince my son to leave his smartphone and go to do something. But I really like this agent to replace people. For example, I would like to have an agent that will convince me or others not to eat the cake, but to eat something healthy. Or we built with the Sheba Hospital in Israel a system that replaces a speech therapist in helping people with brain damage to train and improve their speech capabilities. And we can also use an agent to train people. For example, I'll show you in a minute, we built an automated system that can be used for training people that want to get ready for an interview in the job market. or we build an agent for the Israeli police to train people in interviewing, at least especially young personnel, to train to interview a suspect or other people. Let me just show you a short video of this. So it's in Hebrew. Why? Because the Israeli police... But you have subtitles.
מה השם שלך?
אתה מכיר אותי, יש לך במחשב, אני גמל.
Okay, and so we build the agent that plays the role of the virtual suspect, and his answers depend on the questions that the young police personnel is asking. And this led to a huge European Horizon 2020 project when we tried to train people to collaborate together in interviews, while others, the adversaries are collaborating, etc. We need also, the good guys need to train themselves how to collaborate together. So these are many projects where computer system interact proficiently with people. What is common to all these systems? So the main issue is that in all these systems, we need to predict the user behavior in order to build a good agent. I need to predict whether the human will accept or not accept an offer. I need to know how my son will respond to an argument that I say in the discussion. I need to predict where the adversary will attack. I need to predict how the drivers in the road in another project will react to setting a car in a location, etc. Now, why is it so difficult to predict people decision-making? Well, I always say because people that are upsetting, they ruin my experiments. But really, because they don't maximize expected utility. Why they don't maximize expected utility, I'm not sure. But probably because they are sensitive to context, they lack of knowledge of their own preferences, they affect by complexity, they have problem of self-control, etc. So that made predicting human decision-making very difficult. I would prefer to assume that people are following really nice equilibrium strategy, but this is rarely happened, at least in my experience. So what can we do? So we first start with some data about decision-making of people. Sometimes we have a lot of data, but in many, Google are collecting data for us. But in many cases, we don't have that many examples, as you will see, because collecting decision-making of car drivers, how they respond to our suggestion how to save energy is more difficult. So in some cases, we are using human behavior models that were developed by social sciences as a way to shape our models and to find good features and properties. Then with this, we are using some machine learning method. Many times we need to develop our own machine learning algorithm because of the constraints of the problem. So we have a human prediction model, and then when we have a specific human with a specific data, even if it evolves over time, we can enter it to the model and get some prediction. But this is just the beginning. Having the prediction or having a model of the human is just the prediction. It's just the beginning of the story. Then the main issue is that we have some optimization problem or some game theory setting to solve, because our agent does have some problems that it does have an optimization problem to solve. It does have a goal that we would like it to maximize expected utility or to satisfy the goal. So the idea is to integrate the prediction model of the human into some optimization or some game theory model such that after we solve it, we have some action that the agent should take in the interaction with the human. And usually, if you have some nice virtual human around, it really helps the interaction with people. But this is not our main issues. So, for example, if we are thinking about the automated agent NegoChat that negotiated with people, we had this aspect. We have data that we use both to predict whether people will accept an offer or not. And also we use the data because people were using chats. We need to recognize what they are saying in the negotiation. We also use data and machine learning. But then we had some optimization problem to solve. What will be the best strategy of the negotiation so our agent will get the best result from our point of view? And we also use human behavior models such that it will help in some decision of the agent that we can't solve by solving an optimization problem. So if we just want to see our system, so
I was offered a job at ImagineWeb, and I have been asked to come in and discuss the terms of my employment.
OK, so let me just show you what he's doing.
The logic behind NegoChat is based on two bounded rational theories, anchoring and aspiration adaptation theory. At the start of this negotiation session, NegoChat presents a full offer. While we don't expect the human counterpart to accept this offer, it does provide an anchor, or a basis, for further negotiation offers. The agent incrementally focuses on one issue at a time, based on which issue is the next most important or aspired to. The employer's most important value is salary. NegoChat shows flexibility in negotiating for an aspired value salary and tries to find a counteroffer that yields a similar utility value to itself while incorporating the employer's request for salary.
OK, so that, if you, the young people, if you need to train for negotiating about salary, you can log into the system. It's online and try your, and train yourself. Anyway, so that was one aspect. In negotiation and the cases I show you, the domain was not that complex. We had it well in advance. But in other settings, it's not just we need to predict the human behavior. We need also to predict things about the environment. And again, we need the model. So we need the model for the human, and we need the model for the environment. And again, we have data. We need to collect data on both. We have the machine learning method to build the models. And then it goes into the optimization of the agent. And the agent takes an actions. So I want to present in this talk 2 examples that demonstrate the use of this methodology. One is about providing arguments in discussion, and it's with my student, Ariel Rosenfeld. And the story was like this. People from Intel came to me a few years ago, and they wanted to develop an agent that will whisper in the ear of people when they are doing discussions. And they said, you have this non-monotonic reasoning that was the basic for argumentation theory. Why won't you use argumentation theory to build such an agent? And the student was very excited, and he went, and there are many, many, many papers about beautiful, really nice theories about argumentation. And we read the papers, and we said, OK, we'll use this. But before we use it, I told him, I know that in game theory, game theory is not a good predictive model for people behavior. Before we are using argumentation theory for our model, let's check that people are following one of the series of argumentation theory. So what we did, we took from the literature 6 fictional cases that appeared in the literature of argumentation theory. We collected people from Amazon Turk, and we let them negotiate. And this, you can see it in the format of argumentation theory. You have nodes, which are the, where is this thing? Disappeared. Never mind. You have the nodes are the arguments, and they can attack or support the arguments. And there is some ways in argumentation theory to decide what is a strong argument. And here the wife is saying, let's buy SUV, and the husband, or the other way around, the husband said, let's buy SUV, and the wife said it's too expensive, and we asked him, what will be the next argument you'll say? So you can say, well, SUV is safe, or we said, yeah, it's too expensive because there are taxes, or you can say, I'm taking a loan, or you can say, well, taking a loan, there is high interest. Okay, so what will you say in such a situation? So we collected what people said, and most of them chooses this argument, let's take a loan. And it turned out that any argumentation theory that you use will give very low weight to this argument. And as I said, 35% of the people choose this one, but this is just an example. And this is really low, regardless to what extension you use or numbers or any. So that wasn't that nice. I was very disappointed. The student was extremely disappointed. So I said, well, OK. He said, this is just fictional arguments. Why won't we go and look at real argumentation? So the student Ariel found a database of transcript of arguments people said about various topics, and it shows 2 topics, capital punishments and trial by jury. And this was a database from 1995, and it checked whether the arguments that people said belong to extension. Extensions is the concept in argumentation theory of what are good arguments that will be said in the theory. And it turned out that only less than 45% of the arguments said in the discussion belong to any extension. And that was extremely discouraging, because this was really real discussions. So, yeah, so just to summarize this, we have fictional cases of 142 people. We have transcript of these people, and we have also students that did chat with 72 people doing a chat, and most of them didn't follow argumentation theory. So what can be done? OK, I said, let's use our methodology. What the methodology said, let's try to predict what people will say in the argumentation. This will be the first thing, So we collected data from Amazon Turk and for also computer science students in Israel. And they did both this and others. And we tried to find features about this argumentation. And one thing that we did, the features that we used were based on argumentation theory, like justification that was but we also took features from psychology and also new concepts that we developed, which called relevance, how this argument is close to the previous arguments, looking this as a tree. OK? And then we were able to do quite well. This is us. It depends how many how many times I saw you. So if I saw, for example, 4 responded of the person, I quite well know how to predict the 5th time, the 5th argument that he will propose. And these are other random or as going according to the major, this is MLE. And we did quite well. Interestingly enough, people around, we did it in 2 countries, people from both countries didn't do exactly the same, but I can use the model, let's say the model I learned in the computer science student, and I got a 77% accuracy to the Amazon Turk, and I got 72% accuracy, which is really nice that it's transferable between countries. We did the same thing, prediction in the capital punishment, and we again got quite good prediction model. So, but as I told you, prediction is just the first step. How do I use a prediction to make argument, to suggest to people which argument to say next in the deliberation? So we said we look at different possibility. One is just to offer them the prediction. You know, I will see what is the best prediction, and then I will choose one of them. Well, I was very reluctant to do it because I said, you know, if a person is thinking about an argument, why will he like my argument? But, you know, I don't understand in people. I just understand in predictions. So, OK. So we said the concept of relevance, weakly related. I was thinking that we look at the graph. Each of them is based on some mathematical models, but I'm just summarizing things that are far away from the argument because these are innovative arguments. We have some heuristic of prediction plus relevant. I said, OK, I will say something from the argumentation theory and see if it's left. We compared with not saying anything and with random. So we have 204 participants in these experiments. And you can see this is the one that did the best from the acceptance rates. You know, if I give you a suggestion what to say in the discussion, will you accept my proposal? So this is the first average usage. So the prediction plus relevance did the best. And so I do a prediction, and I have several arguments that can be said. I chose according to relevance. And then there was only relevance that was doing well, and also the prediction. Weakly related, which was, for my surprise, did the worst. I was thinking if there is an argument that I didn't think of, I would like to hear it as a suggestion, but people didn't like it. Similarly, if we are looking at satisfaction of the people from the advice they got, again, they like this one. OK. So I was quite happy with this approach that we can help people in the discussion. But really what I want an agent that can convince people to do something. As I said, you remember the cake and the... So we said we have a methodology. We need human argumentative behavior. A submodel from argumentation. We build a optimization problem, and let's see how we do it. So we started with argumentation series. This is we combine here 2 models. One is a more theory, and one is also based on weights. And each of them gave different possible conclusions. So we chose one of them according to our experience. So this is how the model looks. So we have arguments in the nodes, and we have attacks and support, but we have also weights on the attacks and support. And we also had weights on the argument if it stays by itself. That is a theoretical model. And it has some advantage of this way that we build it. Now, if we want to have it with people, we need to know where these numbers will come from. So So we took 2 domains. One was about convincing computer science undergraduate student to do a master degree. In Israel, you first do a master degree, then a PhD. So that was a good, and also this cake issue. Just that you know, in this experiment, people came to the lab, they said what they want, a bar, a healthy bar, or a chocolate cake, and then we tried to convince them the other way around. And when they left, they got one of things. We brought them to the lab, and they got the cake or the healthy. Well, I'm not sure it's that healthy, but never mind. So first, we collected human dialogues to build these possible trees or graphs for the argumentation theory. And then we also collected questions. We gave people questionnaires about how strong they think the attacks, what they think about argumentation, and we collected a lot of data to build these trees. Interestingly enough, in this argumentation that they let them just to collect data, it turns out that people use 33% of the students used in the argumentation at least 2 arguments that attacked one another. What can I say? So we have argumentation framework, we have human argumentative behavior, and then we used also machine learning to predict some distribution on the arguments that the person will say next, given the last, the sequence of arguments that he said so far. So we use the data also for prediction. So we have all this part. Now we came to the optimization problem. Now this was tough. What do we have? What do we know about these people? We almost don't know anything about them, because what is their argumentation framework? We don't know. What is their, so we build a POM-DP that the nodes are states of our belief of states are the argumentation graph of the person that, and we updated it over time, and because we have observation. The observation is what the argument that the person really said. So this is a good indication about his model of argumentation. And we used all the prediction and probabilities for building the POM-DP. And now, given that we have POM-DP, we solved it, and we got a, well, easy say to solve it, because it was not easy to solve, you know, these huge POM-DPs. And we use a Monte Carlo search tree and some smart optimization problems, solutions to solve the POM-DP. And that gave us the strategy of the agent in the argumentation, convincing people. Did it help? Well, we ran this experiment with new people, of course, not the people that we checked earlier. And lucky to us, we were able to show that in the master degree, we did as well as the people that try to convince their friends. And actually, in the chocolate cake, we were doing better, significantly better than Juven. The baseline, the one that was following some argumentation theory that was proposed for agents, because no one did with humans, didn't do very well. I must say that in general, as you notice, the percentage of our ability to convince another person to change his mind is extremely difficult. And while we are doing at least as good as people, trying to convince people to change their mind is not that easy. Now we have a project where we have 3 people, and each try to change a person that doesn't have an opinion. So if I don't care if I have a cake or a bar, it's easier to convince me to take one of them. But so will 3. So this is the ongoing work. and we'll see how we are doing in this case. So that was one example. I wanted to show you how we develop and use this methodology that we had. I want to show another project where we had also to model the environment. And this has to do with also with robots. And this is a work of also Ariel Rosenfeld and Noah Agmon and Oleg Maximov and Amos Azaria. So think about now, move to another things. Forget about argumentation and discussion. Just think about one person trying to manage some robots. So it can be a soldier, but it can be drones. And these days, with drones, usually, and in robots, you have one person on one drone, or one person that manage if they are doing smart things, even if the drones are autonomous. UAVs, I don't know if you know, there are 2 people on one UAV these days. And the challenge was, can we put one person on autonomous robots that are cheap? And it's really a problem. If you see, this is my lab, and the robots are moving around. And you should come to my lab and try to manage 10 robots. The robots are looking for green balls. So you say, this is autonomous robots. Why do I care? Let the robot move around. But the robots, the problem are they are backing to some places. And sometimes these robots like to get into the ladies' room in my lab. And then going out is quite difficult. And while they can do it eventually, a human operator can easily maneuver them out, and they are on their way to continue searching for the green balls. Or sometimes they went out of battery, sometimes. And in addition, still there are several decisions that people don't want the robot to make, but want that the person will. When they find the green ball, they wanted to get a confirmation that this is really a green ball and not just a green box or something. So the problem is that there is these 10 robots moving around, and the person that is trying to operate them is getting overwhelmed. And given that, the question is, can we have an agent that will support the operator and will help the robots and the operator to get better results? In our case, find more green balls. So this is just that you see the robots. These are the robots. They are looking for this green ball in my lab. And they are very cheap. They cost less than $1,500. And this is the interface of the operator. OK, we'll go back to these robots in a minute. There will be another movie. So agent design, we need a model for the humans. Who is a human? He's the operator. We need a model for the robots, because he's the environment. We don't know how he will behave. So we collected data on the human behavior. We collected data on the robot performance. The idea was that it's really difficult to collect data when the robots are moving around, they're running out of battery, etc. So the interesting thing here in the machine learning point of view was that we collected data from the simulation, and then we deployed it on real robots. So that was quite nice. And then we have an optimization problem to solve, to set and solve, to give the best advice to the operator. What should it do next? That was the advice we gave him. And this turned out to be extremely useful. So we have 150 hours of simulation and 30 human operators that came to the lab. And then after we have the agent, we ran 3 experiments in simulations. But the most interesting experiment was with bringing real people to the lab twice in a week in between. Once they manage the robot by themselves, once they manage the robot with the help of the agent. Half did this first, half did the other thing first, just to be fair to all of them. And the agent really helps. On average, the robot found 7 balls when the operator didn't have the help of the agent, and 14 balls when it did have the help of the operator, the agent. The operator has the help of the, and it's not just that it was on average good. It helped all the people that came to the lab. The agent helped all of them. And I must tell you, I'm not that good maneuvering robots, but we have also quite good operators, and you can try it. It's really helping people doing it. So let me show you another video demonstrating why I have this. I must tell you why we have this video. Because my student, they wanted to do a video to send to each Kai competition on a video for robots. And I said, oh, come on, this has nothing to do with research. But they were very excited. I said, OK, I will give you the money, but don't come to me for anything about this stupid video. And they won first place. So what can I say?
Dispatch,
Quick! There's a student missing in the Middleton section of the campus.
give me the exact location. A unit is on its way.
In disaster environments, both the victims and the rescuers' lives may be in danger. Robot technology can provide solutions. Today's robots are semi-autonomous and require a human operator's help whenever they cannot handle the situation on their own.
Move Agent 3 away from Agent 4. Move Agent 4 away from Agent 5. Manually drive Robot 6 to a
The fast-paced, simultaneous streams of data from multiple robots can be overwhelming and can be a grueling task for a single operator.
Your robots are too close together. Spread them around. Your robots are too close together. Spread them around. Manually drive Robot 6 to a better position. Move Agent 3 away from Agent 4.
Here in Bar-Ilan University, we have developed an intelligent agent that supports the human multi-robot team collaboration. The agent prioritizes the different tasks, filters the robot's signals, and generates warnings, which enhance the operator's situation awareness, thereby allowing him to make better decisions. The agent uses a novel methodology combining machine learning and optimization techniques, which accounts for both the operator's abilities and the robot's performance in real time. Through extensive empirical evaluations, we have shown that our agent was able to significantly enhance the team's performance, which can translate into saving lives.
There it is. We found it. We got it. I'm sending you the exact location now. Dispatch out.
OK. So we actually use this approach in another domain, which is a storage domain where you have robots that bring the items to the operators that pack them. And here the person needs bots to pack and to manage the robots. And this is extremely difficult. We had a simulation about robot shelves, boxes, packing, and et cetera. And the agent was helping the operator. And again, we had here 2 algorithms with solving the optimization problem. And you can see that people are doing extremely better when they have the agent as advisor, as advising what to do. So if I will summarize, we have automated agent can help people, can replace people, and they can be used to train people. I demonstrate a few of these projects that we did. It's difficult task to build this agent, and we need a lot of things. We need machine learning algorithms, we need optimization, we need to understand the interaction and use game theory models. But putting it all together, I'm having fun. Thank you.